welcome to the deep dive. Today we're really getting into the foundations. We often talk about AI, machine learning, all the flashy code.
Right, the algorithms themselves.
Exactly. But underneath all that, there's this, well, elegant mathematical structure.
The real engine room.
Yeah. So our mission today is to unpack what we're calling the trinity of math for data science: statistics, calculus, and algebra. And crucially, why they matter, not just as theory, but practically.
And knowing this trinity, that's what lets you really innovate, I think. You move past just plugging things into libraries.
You actually understand how it works.
Precisely. How and why. That's the key to building something new, or even just properly troubleshooting what you have.
Okay, so let's start with the first one. Algebra. You called it the language of data. What does that mean in practice? Like if I have data points?
Right. So imagine your data, say, features of a house, square footage, number of bedrooms, age. Algebra gives us the tools to represent that. A single house, that's often a vector, like a list of numbers.
Okay, one list for one house.
Yeah. And then if you have, hundreds or thousands of houses in your data set, you stack those vectors up.
And that becomes...
A matrix. Rows are your houses, columns are the features. It's a really neat way to organize everything.
But it gets more interesting, right, with things like matrix multiplication. I hear that's huge in deep learning.
Oh, absolutely huge. It's not just tidy organization. It's the computational workhorse. It's how layers in a neural network talk to each other, how transformations happen.
So why is it so fast compared to, say, looping through data?
Well, that's vectorization. Your computer's processor, especially GPUs, are built for this. They use something called CMD, single instruction, multiple data. Meaning they can do the same math operation, like an addition or multiplication, on many different data points all at the same time, in parallel.
Instead of doing them one.
And by one.
Exactly. Forget for loops for this kind of scale. Vectorization is dramatically faster. It's honestly what makes training massive models even possible today. Got it.
And if you want to understand how these deep networks work, you have to realize data points are never just isolated numbers. They're organized.
So they're like collections of numbers.
Exactly. They're vectors in this massive high-dimensional space. That n-dimensional reality where AI operates, it's the map of the world for the model.
And that map gets really complex, right? I mean, when we move into modern systems, things like video processing, we're not just talking about vectors anymore. We go way past matrices into these higher order tensors.
Yeah, think about a standard RGB image on a screen. You might picture it as a flat grid of pixels, a 2D matrix. But it's actually a rank 3 tensor. It's got height, it's got width, and then it has that crucial third dimension for the red, green, and blue color channels.
So without that third dimension, you'd be losing all the color information, all the context.
You'd be losing almost everything. And to handle these huge structures, you need some serious algebraic power tools. You need decomposition.
Which is just a fancy way of saying we need to break these things down.
We have to. And arguably the most powerful tool we have for this is singular value decomposition, SVD.
Hold on. I've heard SVD can be pretty computationally intense on its own.
Yeah.
So are we just shifting the problem around? What makes it worth it?
Because SVD is like AI's compression artist. It gives us a mathematical guarantee. It finds what are called singular values, which measure the energy or the really critical information in the data.
Okay, so it finds the most important bits.
The most important bits, which means we can get the absolute best low-rank approximation.
So what does that practically mean for, say, a large language model?
It means we can actually deploy it. We use SVD to compress the weight matrices of these LLMs. You can often throw out over 30% of the information and still keep almost all of its reasoning ability.
Wow, that's huge.
It's the only way to make it feasible to run.
All right, this is where it gets really fascinating for me. Okay, so algebra gives us the structure, the language. What about statistics? You framed it as the grammar of insights.
Yeah, if algebra organizes the words, statistics helps us understand the meaning, the story the data is telling. It deals with patterns, relationships, and crucially, uncertainty.
Right. I know, maybe not the most thrilling word, but honestly, it's the bedrock, the compass guiding everything in AI and machine learning.
It really is.
Our plan is simple. Take your sources on stats and ML, pull out the absolute must-knows, and basically shortcut your path to really understanding this stuff. Let's maybe think about it like we're building a customer churn model. Stats is our guide.
That's a great way to frame it. And what's really fascinating is how statistics takes all that raw, messy data and turns it into something reliable, something interpretable.
Right.
It's what makes an AI system trustworthy, not just predictive. It gives us actual confidence, say, in those churn predictions we're making.
Okay, so it's like a universal language then for anyone working with data, whether that's healthcare, marketing, whatever.
Exactly, a common ground.
So let's unpack the main branches. I gather there are two. How do they work together?
Yeah, two main ones. And critically, they aren't really separate things. It's more like a cohesive feedback loop.
Yeah.
You've got descriptive statistics first.
Okay.
That's all about summarizing the data you know. So for our churn example, think calculating the average age of customers who churned or the variation in their contract lengths, the mean, the variance, that sort of thing.
Just describing what's there.
Precisely. Then inferential statistics comes in. It uses samples like our historical churn data to make, reasonable guesses or predictions about the bigger picture, the unknown population of all our customers.
Making the leap from the sample to everyone.
Exactly. And here's the loop. Say our descriptive analysis shows the churn data is really skewed, maybe lots of very new customers leaving. That insight immediately tells us, okay, be careful. We probably shouldn't use certain inferential methods that assume data is nicely balanced, normally distributed.
Right. So it guides the next step.
It guides us towards maybe transforming the data first or using different kinds of statistical tests that don't rely on that assumption. It's synergistic.
Got it. So descriptive stats really kicks off our understanding. It's the core of exploratory data analysis. EDA, right? Revealing things like central tendency mean, median, and how spread out the data is standard deviation.
Absolutely. Think of it as your first diagnostic tool. It flags potential data quality problems before they mess up our churn model.
Like finding errors or weird values.
Yeah, exactly. Things like kurtosis, which tells you if your data has fat tails, meaning lots of extreme values, or the interquartile range, the IQR, that maps the middle 50% of your data. These are great for spotting outliers because they aren't as easily fooled by those extreme values as, say, the simple mean is.
Okay, so it helps clean things up.
Definitely. And that leads to practical steps. Like if you have missing age data, maybe you fill it in with the median age, which descriptive stats help you find reliably. Or using z-score standardization that's scaling features so they all contribute fairly to the model. Or maybe a log transformation if your data is heavily skewed to make it behave better for certain algorithms.
Okay, that makes sense. So we use descriptive stats to understand and prep the data. Now, building on that, we move into inferential statistics, using that feedback loop you mentioned. The goal here is generalizing, right? Making sure our churn model works on new, unseen data, not just the data we trained it on.
Precisely. Generalization is key. And often, people just report a single accuracy score for their model, like 90% accurate. But inferential stats gives us better tools.
Like
Confidence intervals. Instead of just saying 90%, maybe we find a 95% confidence interval for our churn model's accuracy is, say, 88% to 92%. That range gives a much more robust and honest picture of how reliable that model likely is in the real world.
a range of possibilities. I like that.
Yeah. And this is where it gets really powerful, I think. Inferential statistics brings in hypothesis testing. It's basically the scientific method applied to machine learning.
Okay, how does that work?
Well, you start with a default assumption, the null hypothesis, or H0, H dollars. This assumes there's no effect or no difference. For our churn model, H dollars might be customer age has no impact on churn.
The status quo, kind of.
Kinda, yeah. Then you have the alternative hypothesis, H1, H$1, which is what you're actually trying to claim customer age does impact churn.
Okay.
Then you look at your data and calculate a p-value. The p-value tells you the probability of seeing results like yours if the null hypothesis were actually true.
Okay. Probability of the data if H0 is true.
Exactly. And if that p-value is really small, usually less than a threshold called the significance level, often 0.05, it suggests your observed data is pretty unlikely under the null hypothesis. So you reject H$, in favor of H$1.
So you'd conclude age probably does impact churn.
Correct. It's super useful for formally validating which features are actually important for your model, or for A/B testing comparing two different versions of your churn model, maybe using something like a t-test to see if the performance difference is statistically significant, or if it could have just happened by random chance.
That sounds incredibly useful, but also like something you could easily misuse. Which brings us to statistical rigor and potential pitfalls. You mentioned statistical significance. Is that the same as being important in the real world?
Great question. And no, absolutely not. That's a huge pitfall. Statistical significance having a low p-value just means the observed effect is unlikely to be due to chance. It doesn't automatically mean the effect is large enough to be practically significant or meaningful in a business context. You might find a statistically significant difference that's actually tiny and irrelevant.
Okay, so don't just chase low p-values.
Definitely not. And another big one is misunderstanding the p-value itself. A p-value of 0.05 doesn't mean there's a 5% chance the null hypothesis is true. Remember, it's the probability of the data, assuming the null is true. Subtle, but important.
Right, the condition is key.
And then there's the multiple comparisons problem, or sometimes called the multiplicity mess. Basically, if you run lots and lots of statistical tests purely by chance, you're going to get some statistically significant results, even if nothing real is going on.
Like testing dozens of features for the churn model.
Exactly. Imagine testing 20 features where actually none of them truly affect churn. With that standard 0.05 significance level, you'd still have roughly a 64% chance of finding at least one feature looks significant just by random luck.
Yeah, okay. That could lead you to put useless features in your model.
Precisely. It contributes to overfitting, building a model that learns noise instead of the real signal. That's why it's crucial to also report the effect size. This tells you the magnitude or strength of the effect, not just whether it exists statistically. It gives you that practical perspective.
Okay, so p-value plus effect size gives a fuller picture. It seems clear then that descriptive and inferential statistics really work hand in hand. You need both for solid data science.
Absolutely indispensable. From that initial look at the data with descriptive stats, right through validating your final churn model with inferential methods, statistics ensures integrity.
So it keeps everything honest from start to finish.
Yeah. So what does this all mean for you listening? I think mastering these statistical foundations is what really separates someone who can just use ML tools from someone who's a true expert.
Building things that actually work reliably.
Exactly. It lets you build models that aren't just performant on paper, but are genuinely robust, reliable, and crucially interpretable. And that really shapes the entire future of trustworthy AI. So maybe consider, how does applying this level of statistical rigor change how you approach your next data project?
Makes perfect sense.
Yeah.
Okay, Trinity Part 3. Calculus, the engine of learning. Why engine?
Because calculus is fundamentally about change, how things change in relation to each other. Think of your car's speedometer. It's showing the rate of change of distance over time. That's calculus.
So how does that apply to a model learning?
Well, models learn by adjusting their internal parameters to get better predictions. Calculus helps us figure out how to adjust them efficiently. We start with differentiation. For one variable, the derivative tells you the slope, the instantaneous rate of change.
Like how house price changes just with square footage.
Right. But models usually have tons of variables. That's where the gradient comes in. It's like a multi-dimensional derivative.
A compass.
A compass, yeah. It points in the direction where things are changing the fastest, usually, where the model's error is increasing most steeply. Imagine you're blindfolded on a hillside. The gradient tells you which way is straight uphill.
Okay, so if the gradient points to where the error gets worse...
You go the opposite way. And that's the core idea behind gradient descent.
The ball rolling down the hill analogy.
That's the one. You calculate the gradient of your error, take a small step in the opposite direction, recalculate, take another step, and repeat. You iteratively roll down the hill towards the point of minimum error.
And models use this constantly during training.
Constantly. A key example is backpropagation in neural networks. It uses the chain rule from calculus to efficiently calculate how much each connection in the network contributed to the final error.
So it knows exactly how to adjust everything.
In a very clever, calculus-driven way, yes. It distributes the error signal backwards through the network.
Wow. Okay, so bringing it all together quickly for our house price example.
Yeah.
Algebra structures the house data in matrices.
Yep.
Calculus, through gradient descent, finds the best settings for the model by minimizing the prediction error.
Right. It tunes the engine.
And statistics tells us how good the predictions are, measures the uncertainty, and validates the whole thing.
Exactly. They're completely interwoven. Algebra provides the language, statistics, the grammar for understanding, and calculus the engine for learning and optimization.
A really powerful combination.
It truly is. And understanding that interplay, the why behind just running the code, that's where real mastery lies. It's about building AI you can actually trust because you understand its foundations.
So, a final thought for everyone listening. If you move beyond just using the pre-built tools and really grasp this mathematical bedrock, what currently complex problem could you start to genuinely tackle? Something to think about. Welcome to the deep dive. Ever wondered how intelligent systems learn complex tasks? I mean, not from perfect instructions, but purely by experiencing their world.
Right.
We're doing a deep dive into vector embeddings. This is really the quiet engine behind so much of modern AI.
It really is. We're talking about how machines go from just seeing data to, well, understanding abstract ideas, turning them into something measurable.
Right. Our mission today is to unpack how machines learn the essence of meaning.
It's a fascinating concept. Think of it like this. An embedding is basically a coordinate, a point on this huge multidimensional meaning map.
A meaning map, okay.
Yeah. And on this map, things that are similar in the real world, their points, their vectors are close together. So king and queen might be neighbors.
But king and, say, apple would be miles apart.
Precisely. Worlds apart. The distance itself represents semantic similarity, or lack thereof.
And this isn't just a nice idea, right? This map is something machines can actually work with.
Absolutely. By turning concepts into these numerical vectors, machines can use tools like, linear algebra to perform calculations. It lets them process all that messy, unstructured stuff, text, images, even audio.
So it's like giving them a mathematical language to understand our kind of fuzzy, complex world.
You got it. And it's crucial because, well, the older methods just couldn't do this. Think about one-hot encoding.
Ah, yeah, I remember that. Everything gets its own column, right? A 1 if it's present, 0 if not.
Exactly. Super sparse. And it meant every single word or category was treated as completely independent. Cat was just as unrelated to dog as it was to car.
Which is obviously not how language or the world works at all. It's like these isolated islands of meaning.
Totally. No bridges. Then you had things like TF-IDF, bag of words. They tried to focus on word frequency.
Okay, so slightly better, maybe, counting words.
A bit, but still fundamentally flawed. They were stuck on keywords. So if you searched for feline companions,
it wouldn't necessarily find stuff just talking about cats because the exact words didn't match.
Right. It missed the concept. The breakthrough with embeddings was moving beyond just keywords to actual semantic understanding, meaning.
And that led to some really cool insights, didn't it? The vector arithmetic thing.
Oh, yeah, the classic aha moment. The idea that you can take the vector for king, subtract the vector for man, add the vector for woman.
And you end up somewhere really close to the vector for queen.
Exactly.
That's incredible. It shows the model isn't just memorizing, it's learning these abstract relationships like gender or capital cities as actual directions in this meaning space.
That's the core idea, is learning the structure of meaning. So once we had that, the next step was, naturally, how do we make these embeddings even better? Which brings us to their evolution.
From static to contextual.
But there's always a trade-off.
Let me guess. Computing power.
You nailed it. Static embeddings are faster, less demanding. These contextual models, they need serious resources. They're slower, more expensive to run, but the accuracy and nuance you get are significantly better.
Makes sense. You pay for the sophistication, and this sophistication powers a lot of things we use daily, right?
Absolutely. This is where you see the real-world impact. Semantic search is a huge one, instead of just matching keywords.
It understands what you mean. So if I search for running shoes for flat feet,
it won't just show you any random sneakers. It understands the concept of flat feet and arch support and suggests motion control shoes. It gets the intent behind the words.
Okay, that's clever. And recommendations too, like on streaming sites or shopping.
Yep. They map your preferences and items into the same vector space. Things you might like are simply closer to you on that meaning map.
And it's not just text anymore, is it? I've heard about multimodal stuff.
Right. Embeddings work for images, audio, even combining them. Models like CLIP can understand that the phrase, a picture of a cat, should be semantically close to an actual image of a cat in that vector space. It's bridging different types of data.
Wow. Okay, so they're incredibly powerful. But are there downsides? Challenges?
Definitely. We mentioned the computational cost. That's a big practical hurdle. Training and deploying these state-of-the-art models is expensive.
And what about bias? I've heard that AI models can pick up societal biases from the data they're trained on.
That's a critical issue. Embeddings learn from vast amounts of human text and data. If that data contains biases, say associating nurse more with female pronouns and engineer more with male pronouns, the embeddings will learn those associations.
So the model isn't being malicious, it's just accurately reflecting the biased patterns in the data it learned from.
Precisely. It's learning undesirable human patterns, and that's a huge ethical consideration. There are efforts to mitigate this, like adjusting how the models learn or trying to debias the vectors afterwards, but it's an ongoing challenge.
A really important one. So, wrapping this up a bit, we've seen how this quite elegant idea, turning complex stuff into numbers on a map, has become fundamental to AI.
Yeah, from search to recommendations, they're everywhere, powering so much. This conversion to a universal numerical language is key.
But looking ahead, and this is maybe something for you, our listener, to think about, is this enough? Is a single fixed-length vector, however sophisticated, ultimately going to be limited? Can it really capture everything needed for truly deep reasoning or, say, complex instruction following in AI?
That's the million-dollar question, isn't it? When we hit the limits of what a single vector can represent, what comes next? What new ways of encoding meaning might we need?
Something to definitely mull over. Vector embeddings are powerful now, but the quest for true understanding continues.
Today, we're jumping into deep learning, or DL, which is, the engine behind pretty much every major AI breakthrough we see.
From your phone's camera to the huge language models.
Exactly. So our mission today is to get past the buzzwords and really figure out why this specific type of AI became so incredibly powerful.
And it's interesting because at its core, deep learning is really defined by its architecture. It's just multiple layers of computation, kind of inspired by the brain.
Inspired by the brain, right.
But the real game changer isn't the structure, it's what it can do. It can take in huge, messy piles of unstructured data images, text, sound, and just figure out the patterns for itself.
So it's this idea of depth then. How does just adding more and more layers actually change what the model can learn?
It enables something called hierarchical feature learning. You can think of it like a pyramid. The first few layers learn really basic stuff.
Like edges and colors in a picture.
Exactly. Simple edges, textures, that sort of thing. But then the deeper layers start combining those little pieces into much more complex concepts. Like it'll put edges together to see the curve of a wheel or the shape of an eye.
I see. So it builds understanding.
It builds understanding layer by layer. And the data on this is just undeniable. We saw a 152-layer network outperform an 18-layer one on the ImageNet challenge by almost 10 percentage points?
That's a huge difference. But if the core math, this thing called backpropagation, was figured out way back in the 1970s, were we just waiting around for better computers? Did we miss the boat for 30 years?
That's the million-dollar question, isn't it? And the failure wasn't really algorithmic. I mean, the math was solid. It was a resource bottleneck.
A resource bottleneck.
Yeah, they had this beautiful mathematical engine, but they had absolutely none of the fuel. They didn't have the massive data sets or the raw compute power. It was like having a Ferrari engine, but only bicycle fuel to run it on.
Okay, so the fuel had to arrive, and that was the ImageNet project, right?
That was the catalyst. Between 2009 and 2012, Fei-Fei Li's team saw this exact problem, this data deficit, and they built ImageNet. We're talking 12 million labeled images.
A massive undertaking.
And that set the stage for what we call the AlexNet moment in 2012. They used GPUs, graphics cards, to just power through that data. And it didn't just improve the result, it slashed the error rate. It proved that scaling up data and compute wasn't just helpful, it was everything.
So they had the fuel and the engine. What was next?
Well, even with the power, the process was still a bit inefficient. It needed a better lubricant, you could say. And that innovation was the rectified linear unit, or ReLU.
ReLU.
Sounds technical. But the idea is simple. It's just a more efficient on-off switch for the artificial neurons. It stopped the deep networks from seizing up during training, which is what made training a 152-layer network even possible.
Okay, that makes sense for images. But what about something messy, like a conversation or just a long piece of text? I've heard about this vanishing gradient problem.
Right. With sequential data, older networks, they had terrible short-term memory. A signal from the beginning of a paragraph would just fade away or vanish by the end.
So it would forget the context.
Completely. And that's what led to things like LSTMs and GRUs. They have these spiralized little mechanisms, like a forget gate, that let the network very deliberately decide what old information is important to keep. That finally cracked the long-term memory problem.
And that whole line of thinking led us to where we are now with the transformer architecture from 2017. What was the big leap there?
It completely threw out sequential processing.
Yeah.
Instead of reading word by word, the transformer uses something called the self-attention mechanism to look at every word at the same time. It's massively parallel.
And self-attention is the core of every big language model today. So what is it in simple terms?
The best analogy is that for every single word, it runs a quick search across the entire sentence to see how relevant every other word is. It uses these things called query, key, and value vectors to weigh connections.
So it creates a global context.
An enforced global context instantly. It knows how the first word relates to the last word, all at once. That's its superpower.
So if you put it all together, deep learning's success wasn't one thing.
No, it's a perfect storm. It's a symbiotic relationship between, the mathematical insights from decades ago, the explosion of big data, and the sheer power of modern hardware like GPUs.
So here's the final thought to leave you with. While these DL models give us incredible performance in everything from medicine to self-driving cars, their complexity often turns them into complete black boxes. We know they work, but we don't always know why.
That's the trade-off.
And that's the critical challenge facing everyone in this field. We're constantly choosing performance over interpretability and figuring out how to balance those two things. Well, that's the next great deep dive. Welcome to the deep dive. Today, we're really going to get into supervised learning algorithms, our mission. Cut through the noise, the jargon, and give you some solid practical insights. Think of it like learning with flashcards, maybe. You see a question, you learn the answer, and eventually you can handle totally new questions.
That's a great analogy. Yeah, supervised learning, it's a huge part of machine learning. It's all about using labeled data where we already know the right answer to train a model. The model learns to map inputs to outputs. But, and this is crucial, it all hinges on the data. Garbage in, garbage out, as they say. Data quality is absolutely paramount.
Okay, right. So garbage in, garbage out. Let's unpack these models. If we're starting simple, where do we begin? Linear regression, maybe? That's the one where you're basically trying to draw the best fitting straight line through your data points on a graph, like pulling a string taut across them, minimizing those distances.
Exactly, yeah. The least squares method, technically.
Yeah.
Linear regression is, well, it's beautifully simple, very interpretable. We call it a white box model because you can see exactly how it's making predictions. Think about predicting salary based on years of experience. You can literally see the weight it gives to experience. Its strength is that clarity.
But it has limits, right? It assumes things are, well, linear.
Precisely. It assumes a straight line relationship, and the real world is often much messier than that. Doesn't always fit a neat line.
Okay, so if linear regression handles continuous stuff like salary, what about predicting categories like yes or no, spam or not spam? That's logistic regression, isn't it?
That's right. And what's fascinating here is how it does classification. It takes a linear model's output, sometimes called log odds, but then squishes it. It uses this function, the sigmoid function, that looks like an S shape. It forces the output into a probability, a value between 0 and 1.
Ah, okay. So not just yes or no, but maybe 95% chance this is spam, or a specific risk percentage for a disease.
Exactly. That probabilistic output is incredibly valuable for making nuanced decisions. Much more info than a simple binary yes-no.
Makes sense. Now, what if the relationships in the data aren't straight lines or simple S-curves? What if it's really complex nonlinear stuff? Decision trees come in here, yeah. They seem more like flowcharts, asking a series of if this, then that questions to split the data.
Yep, that's the core idea. It recursively partitions the data, asking questions at each step like, is feature X greater than value Y? Trying to create groups or leaves that are as pure as possible, meaning ideally each final group contains data points of only one class. We measure that purity or lack thereof using things like Janey impurity, trying to minimize the mix-up.
And the big plus is you can follow the path, right? See the logic.
Totally. Very interpretable. But, here comes the downside. They were notoriously prone to overfitting.
Overfitting? That's like memorizing the training examples, including all the random noise, instead of learning the actual underlying pattern.
You got it. Like a student who memorizes answers but doesn't understand the concepts. It performs great on data it's seen, but falls apart on new, unseen data. Doesn't generalize well.
That sounds like a big problem. So how do we stop these models from just memorizing everything? How do we, discipline them?
That's where regularization comes into play. This is really interesting stuff. Regularization basically adds a penalty to the model based on its complexity, usually related to the size of its coefficients or weights.
A penalty for being too complex?
Sort of, yeah. Two common types are lasso, or L1, and ridge, or L2. Think of it geometrically. Lasso uses a penalty that often forces some coefficients to become exactly 0.
0. So it kicks features out.
Exactly. It performs feature selection, which is super useful. Ridge, on the other hand, uses a penalty that shrinks all coefficients towards 0, but rarely makes them exactly 0. It's good for handling situations where your input features are highly correlated.
Okay, so ways to keep models in check. What about combining models? I hear about ensemble techniques, the idea that lots of simple models together can be better than one complex one, the wisdom of crowds.
That's a perfect way to put it. Ensemble methods combine multiple weak learners to create a single strong learner. And there are two main flavors. First, there's bagging. Think of random forest. It builds multiple decision trees independently on different subsets of the data and then averages their predictions or takes a majority vote. It works in parallel, reducing the model's variance, making it less sensitive to the specific training data.
Okay, parallel processing. What's the other flavor?
That's boosting. This is sequential. Imagine a student working with a tutor. The first model tries to solve the problem, gets some things wrong. The next model focuses specifically on the mistakes the previous one made. Each subsequent model pays more attention to the errors, step by step, trying to reduce the overall bias. Gradient boosting is a key example here.
And isn't there one called XGBoost that always seems to pop up?
Yes. XGBoost is essentially a supercharged, highly optimized version of gradient boosting. It's got built-in regularization, handles missing data well, and is computationally very efficient. That's why it often dominates data science competitions. It's very powerful.
Got it. Okay, one more I wanted to ask about. Naive Bayes. The name naive sounds not great. Why naive?
Yeah, it does sound a bit suspect. It's based on Bayes' theorem, which is solid probability theory, but it makes a very strong naive assumption that all the input features are independent of each other given the class.
Independent. But features in the real world are often related, aren't they? How can it work if it assumes something that's usually wrong?
That's the counterintuitive part. It turns out that even though that independence assumption is almost always technically false, the algorithm often works surprisingly well in practice. Especially for things like text classification, spam filters are a classic example. Its simplicity makes it incredibly fast and efficient computationally. You just need to handle potential issues like the zero frequency problem. What happens if you see a word in testing you never saw in training? But there are simple fixes for that.
Wow, okay, so we've covered quite a range, from simple lines to complex ensembles and even naive approaches. When you're faced with a problem, how do you choose? It sounds like there's no single best algorithm.
Absolutely not. There's no silver bullet. It's always a trade-off. You have models like linear regression, logistic regression, decision trees, even naive Bayes. They tend to be more interpretable. You can peek inside and understand why they're making certain predictions. Then you have models like random forests and XGBoost, which often give you higher predictive accuracy, sometimes significantly so, but they can be more like black boxes. Harder to understand the internal logic.
So it depends on the job, interpretability versus accuracy.
Exactly. What does your data look like? What are your project's priorities? Do you need to explain the why behind predictions, maybe for regulatory reasons? Or is pure predictive power the main goal? That balance dictates your choice.
What a fascinating journey, really. From finding the best line to combining weak learners into something powerful. It's this constant balance, isn't it? Simplicity versus complexity.
It really is. And maybe here's something for you, the listener, to chew on. That complexity we often chase for better predictions. It frequently comes at the expense of being able to clearly understand why a decision is being made. So it really pushes us to think critically. How much transparency are we willing to sacrifice for performance? In machine learning, and maybe in other decisions too.
That's a great point. How much transparency versus performance? Definitely something to think about in how we all process information and tackle problems. Today, we're jumping into unsupervised learning algorithms. These are like data detectives finding hidden patterns, but without any predefined answers. Our goal: break these complex ideas down, Feynman technique style, so you really get what makes them tick.
That's a great way to put it. You know, I often think of Sir Isaac Newton and the apple. He didn't get data labeled gravity. He just observed, asked questions, and inferred the laws himself. That's unsupervised learning in a nutshell. It's discovery, finding structure before you even know exactly what prediction you want to make.
That really frames it well.
Yeah.
So, okay, how do we start finding these patterns? Clustering seems like a big one, right? Grouping similar things together.
Absolutely. And K-means is probably the most famous. Think center of the crowd. It finds center, points towards it, recalculates the center, this little two-step dance. You see it everywhere. Customer segmentation, even image compression, grouping similar colors.
K-means sounds pretty efficient then, but what are the catches? Like you have to tell it how many groups, and do they need to be, I don't know, certain shapes?
Yeah, exactly. It's fast, but you do need to specify K, the number of clusters up front. And it definitely prefers clusters that are kind of spherical and roughly the same size. If your data looks different, maybe long and thin clusters or different sizes, k-means might struggle a bit.
Okay, so if k-means has those limits, what's next? You mentioned DBS scan before, something about density?
Right, DBS scan, it takes a totally different approach. Instead of centers, it looks for dense regions. It uses two parameters, epsilon, that's like a search radius around a point, and min-peats, the minimum number of neighbors needed to be considered core. This lets it find clusters that aren't just round, they can be any shape. And crucially, it can identify points that are all alone as noise.
Noise, so like outliers, things that don't fit.
Exactly, which makes it fantastic for anomaly detection. Think finding weird credit card transactions, that sort of thing.
And you don't need to tell it k beforehand. That sounds really useful.
No k needed, which is a big plus. The trade-off. Tuning epsilon and min ports can be, well, a bit tricky sometimes. Especially if you have lots and lots of dimensions, density gets weird.
Right, high dimensions. We should come back to that. But first, there's another clustering type, hierarchical.
Ah, yes, hierarchical clustering. Think of building a family tree, but for your data points. It starts with every point as its own tiny cluster, then merges the closest ones step by step. You get this visual called a dendrogram, the tree diagram.
Okay, like a branching structure showing who merged with whom.
Precisely. And different linkage methods decide what closest means when you merge clusters. Like Ward's method tries to keep the merged clusters nice and evenly sized, so it's good for things like biological taxonomy or, again, market segmentation maybe.
And the cool thing with the dendrogram is you can kind of decide later how many clusters you want just by looking at the tree.
That's a huge advantage. You run it once, get the tree, then decide where to cut it to get your clusters. But the downside is it can get computationally heavy. For really massive data sets, tracking all those potential merges takes time. It starts with every point as its own tiny cluster, then merges the closest ones step by step. You get this visual called a dendrogram, the tree diagram.
Okay, like a branching structure showing who merged with whom.
Precisely. And different linkage methods decide what closest means when you merge clusters. Like Ward's method tries to keep the merged clusters nice and evenly sized, so it's good for things like biological taxonomy or, again, market segmentation maybe.
And the cool thing with the dendrogram is you can kind of decide later how many clusters you want just by looking at the tree.
That's a huge advantage. You run it once, get the tree, then decide where to cut it to get your clusters. But the downside is it can get computationally heavy. For really massive data sets, tracking all those potential merges takes time.
Okay, so that covers finding groups. But what if the data itself is just too much? Too many features, too complex to even start?
That's a perfect lead-in to dimensionality reduction. We need ways to simplify. And the classic here is principal component analysis, PCA. Its goal is to find new axes, principal components that capture the most variance, the most information in your data. Imagine squashing your data onto a line or a plane while losing the least amount of spread.
So it simplifies things, makes it easier to maybe visualize or process, like for image compression again.
Exactly. Visualization, compression, and it's a key weapon against the curse of dimensionality.
Okay, PCA sounds powerful for simplifying. But interpreting those new principal components, are they easy to explain? Like, what do they mean?
That's the rub. They're mathematically efficient, capturing variance, but they're abstract combinations of your original features. So telling a business user what principal component 1 means can be tricky. It shows separation, but maybe not the why in simple terms. And just quickly, while we're here, it's worth mentioning LDA, linear discriminant analysis. It also reduces dimensions, but it's actually supervised.
Ah, right. So LDA needs labels. How does its goal differ from PCA then, if both reduce dimensions?
Totally different goal. PCA just looks for the directions of maximum variance in the data, regardless of labels. It's exploratory. LDA, because it has the labels, specifically tries to find the dimensions that best separate those known classes. Think improving a classification model, like for credit risk, where you know who defaulted and who didn't. PCA explores, LDA separates known groups.
Got it. PCA for exploring structure, LDA for enhancing classification. Okay, let's shift to some maybe foundational ideas that pop up across these methods.
Sure, like k-nearest neighbors, KNN, usually taught as supervised, right? Find the k closest labeled points and vote.
Yeah, for classification or regression, but unsupervised.
Well, the core idea of finding neighbors is super useful without labels, too. For anomaly detection, if a point's average distance to its k-neighbors is really high, maybe it's an outlier, right? It's far from everyone. Or even filling in missing data, look at the values of the nearest neighbors, and estimate.
So the basic mechanism of finding neighbors can be used in creative, unsupervised ways. That's neat.
It really highlights understanding the core idea. And speaking of neighbors and distances, that brings us to the curse of dimensionality you mentioned.
Right. The curse. What actually is that? Sounds ominous.
It is, a bit. Basically, as you add more and more dimensions or features, the space your data lives in gets incredibly vast and empty, really sparse. Counterintuitively, everything starts to seem far away from everything else. The concept of a close neighbor starts to break down.
So distance-based algorithms like KNN or even clustering, they just stop working well.
Pretty much. The distance has become less meaningful, which is why dimensionality reduction like PCA isn't just nice to have. Sometimes it's almost essential to make these algorithms work effectively in high dimensions.
Makes sense. And underlying all these distances, how we measure closeness itself matters, right? The metrics.
Absolutely fundamental. Euclidean distance is your straight line, as the crow flies. Good baseline, but sensitive to outliers. Assumes things are kind of Gaussian. Manhattan distance is like city blocks, only horizontal and vertical moves. Less sensitive to outliers, maybe better if data seems more Laplacian. And then cosine similarity just cares about the angle between data points, not the magnitude. Great for text data, where word counts might vary wildly, but the topic, the direction, is similar.
Wow, so choosing the metric isn't trivial. It's a core assumption about the data.
It really is. It shapes what similar means.
Okay, so with all these methods, k-means, DBS-scan, PCA, how do you tune them? In supervised learning, you have the right answers to check against. Here, you don't. So how do you know if it's good?
That is the million-dollar question in unsupervised learning. There's no single right answer or objective score like accuracy. It comes down to a mix of things. Heuristics, like looking for stable clusters. Domain knowledge. Does this grouping make sense in the real world? And ultimately, human judgment. Can you, the analyst or the user, derive useful insights or value from the patterns it reveals? The data scientist becomes more of a facilitator for discovery.
So we've really dived deep into this world of unsupervised learning. It's clearly more than just algorithms. It's a whole mindset about exploration and discovery in data.
Exactly. That lack of ground truth isn't just a challenge, it's the whole point, in a way. It's the opportunity. It lets us find structures, signals, connections in huge amounts of unlabeled data that we might never have even thought to look for. Truly hidden insights.
So maybe the final thought for you listening is, knowing these hidden structures exist, how might that change the kinds of questions you even think to ask about the world around you? Something to ponder.
Today, we're plunging into reinforcement learning, RL. It's this really fascinating area of machine learning. It's all about how agents learn to make sequential decisions, basically through trial and error.
Exactly. And our mission for you in this deep dive is, well, to cut through the noise, unpack the core mechanics of RL, and clarify why it's such a game changer for problems demanding optimal decisions over time. You should get some real aha moments about how these systems learn from often quite delayed feedback.
Okay, let's unpack that. Our sources really stress that reinforcement learning is, at its heart, concerned with an agent making a sequence of decisions.
Yeah, in an environment that's dynamic, maybe uncertain.
Right, and the goal is always maximizing some kind of cumulative reward signal.
And what makes RL so potent, I think, is that unlike systems you train on static pre-labeled data sets.
Like in supervised learning.
Precisely. RL actively discovers the best behavior through continuous interaction, trial and error. It's really uniquely suited for that sequential decision-making where the impact of an action isn't always immediately obvious.
Let's try and ground this. The classic analogy is training a dog. Right? The dog's the agent, the living room is the environment. Actions like sit, get a reward, maybe a treat. But, for our deep dive, let's maybe pivot instantly to something more complex.
Yeah.
Think about an autonomous drone navigating a forest.
Okay, yeah.
Here, the state isn't just dogs sitting by the door. It's like this high-dimensional input of LiDAR data, GPS, camera feeds, much more complex.
That interactive loop, though, that defines RL, you always have these 5 core components.
Yeah.
The agent that's the decision maker,
Got it.
The environment, the external world it interacts with, the state that's its current perception of the world, like that drone's sensor data,
Right.
The action, what the agent chooses to do, and the reward, which is that immediate numerical feedback, good or bad.
Okay, so those are the building blocks. Agent, environment, state, action, reward. But how does it actually decide what action to take in a given state? That gets us to the policy, right?
Exactly. The policy is essentially the agent's master strategy. Think of it as a map from states to actions.
A map, okay.
And policies can be deterministic, like always do this action in this state, or they can be stochastic.
Stochastic. So probabilistic.
Yeah, providing a probability distribution over actions. Deterministic is fine if the world is perfectly predictable.
But it rarely is.
Right. So stochastic policies are vital. They help with exploration, trying new things, and they're crucial in, say, adversarial settings like poker. If you're too predictable, you get exploited.
Okay, that makes sense. You need some randomness.
A bit, yeah, to learn robustly.
So building on that policy idea,
Yeah.
if a reward is like a single paycheck you get right now, then the value function sounds like it's more about the long game, like a financial forecast for the next decade, the total expected reward down the line.
That's a great way to put it. It's this forward-looking perspective. It's often formalized by something called the Bellman equation, which is, well, it's really the backbone of many RL algorithms.
Why is it so central?
Because it lets us break down this huge, complex, long-term optimization problem into smaller, recursive steps. It essentially says the best value of being in a state now is the immediate reward you get, plus the discounted best value of whatever state you end up in next.
Discounted, meaning future rewards are worth a bit less than immediate ones.
Exactly. It encourages prioritizing achieving goals sooner rather than later, and it also keeps the math as manageable. It helps the agent weigh long-term gains against short-term ones.
So as the agent is learning, refining his policy, figuring out these values, it hits this classic problem, right? The exploration-exploitation dilemma.
Ah, yes. The ultimate dilemma, isn't it? It's like finding a restaurant you absolutely love.
Yeah.
Do you just keep going back, exploiting that knowledge? Or do you explore that new place across town that might be even better but could also be terrible?
Right. The risk versus the known reward.
Precisely. That balancing act. Exploiting what you know works versus exploring new possibilities for potentially much bigger payoffs. Getting that balance right is absolutely core to learning optimally in RL. Too much of either isn't good.
Okay, that provides a really good picture of the mechanics inside RL. But, stepping back, we already have supervised learning, unsupervised learning. What is it fundamentally that makes RL stand out? What problems can it solve that the others can't really touch?
The key differentiator, I'd say, is the credit assignment problem.
Credit assignment. Explain that.
Okay. In supervised learning, the feedback is instant. You show it a cat picture, it says dog, you immediately say, no, that's a cat. The feedback is right there, tied to that specific input.
Got it. Direct link.
But in RL, imagine playing chess. You make a brilliant move on turn 10, but you might not actually win the game until turn 50. The profound challenge is figuring out which of the many actions you took before that win were actually responsible for it. Was it that move on turn 10, or something on turn 35, or a combination? Assigning credit back in time to the right actions. That's tough.
Because the reward is so delayed.
Exactly. And this is precisely why techniques like Q-learning and temporal difference learning, or TD learning, are so fundamental in RL. They give us elegant ways to propagate that delayed reward signal back through the sequence of states and actions, even if we don't have a perfect model of how the environment works.
Oh, it's like learning a really complex skill.
Sequential delayed feedback and the algorithms designed to handle it, that's what truly makes RL unique.
And we see this playing out spectacularly in video games, right? They become this amazing sandbox for RL.
Oh, absolutely. I mean, from classic Atari games like Miss Pac-Man's Simple Actions, but millions of possible game states all the way up to DeepMind's AlphaGo Mastering Go.
Which has an astronomical number of states.
Astronomical. And OpenAI's Dota 2 AI. These RL agents learn strategies that are often at or even beyond human level. They frequently use deep neural networks now to handle the sheer complexity, approximating those policy and value functions by basically playing millions and millions of simulated games.
You mentioned something earlier about intentional imperfection in commercial games. That sounds counterintuitive. Isn't RL all about finding the optimal strategy? Does needing imperfection mean RL has limits? Or is it something else?
That's a really sharp question. It's less about a limitation in RL's ability to find the mathematically optimal path, and more a challenge in defining what optimal means when humans are involved. An AI that finds some obscure loophole to win every single time might be optimal according to its reward function, but it would be incredibly boring or frustrating for a human player.
Right, ruins the fun.
Exactly. So it's more an adaptation. Game designers carefully shape the reward signals, or sometimes they combine the learned RL behaviors with more predictable scripted actions. The goal shifts from pure mathematical optimality to creating an opponent that's engaging, challenging, maybe even feels fair, even if it's not technically playing perfectly. It reflects that the goal is often more nuanced than just winning.
That makes a lot of sense. So wrapping up then, reinforcement learning gives us this distinct, really powerful way for agents to learn the best policies just through interacting with their world.
And brilliantly balancing that need to explore new things with exploiting what already works, all to maximize that cumulative reward over the long haul.
And it's clever ways of tackling that credit assignment problem, handling delayed rewards, and adapting on the fly.
Yeah, it means the applications are just exploding well beyond games. We're seeing it increasingly in robotics, personalized medicine, complex financial modeling, sophisticated recommendation systems. It's really versatile.
We have covered a lot today. So next time you see an AI making what looks like smart sequential decisions, maybe pause and consider that intricate dance. It's doing actions, states, rewards, exploration, exploitation, constantly learning.
It really is a fascinating process.
And maybe think about this. How might understanding this exploitation balance change how you approach learning new skills, or even making important decisions in your own life? Something to chew on. Okay, let's get into it. We're doing a deep dive today, really aiming for, total mastery of the core ideas in machine learning, AI, ML, DL. The goal is to get you up to speed fast so you can confidently follow pretty much any technical chat on the topic.
Right, and to get that solid footing quickly, it helps to start with the hierarchy. I like the Russian dolls analogy. Think of AI as the biggest doll. It's the grand goal, right? Creating intelligent systems.
Okay.
Then nested inside, you've got ML, machine learning. That's the main way we're actually doing AI nowadays. Learning patterns straight from data.
And the innermost doll.
That's deep learning, DL. It's basically a very powerful, sort of sophisticated tool within ML that uses these big, deep neural networks to do the learning part.
Got it. So ML is kind of the engine driving progress in AI. And its big contribution is finding these complex patterns, and this seems crucial, being able to generalize them, to apply them to new stuff it hasn't seen.
Exactly that. Generalization is absolutely key. And how it learns those patterns, well, that really depends on the data you give it and the kind of feedback it gets. Our mission, to cut through that jargon, we're focusing on the hierarchy, the key trade-offs, and the why behind it all.
Exactly. We want to give you that mental map you need for mastering generalization.
Okay, quick rundown on learning paradigms. Supervised and unsupervised seems straightforward data-driven. Labels or no labels.
Right. Classification, regression with labels, clustering without, dataset focused.
But reinforcement learning, that's the odd one out.
Totally different beast. It's not about a fixed dataset. The agent learns by doing, interacting with an environment, getting rewards, getting punished, basically.
Yeah.
Think robotics, game AI.
So the interaction part, is that why it's maybe trickier to get working reliably compared to supervised?
Oh, definitely. Much less stable sometimes because the target isn't fixed. But okay, let's stick with supervised models for now and hit the absolute core issue, generalization.
Right, making sure the model works on new data. And this is where the bias variance trade-off comes in. You said this is critical.
The most critical concept for generalization, I'd argue. It governs performance on unseen data.
So let's break down the total error. What are its parts mathematically?
Okay, so it's bias squared plus variance plus, and this is important, the irreducible error.
Irreducible error.
Yeah, think of it as the baseline noise. The randomness in the data itself that no model, no matter how good, can eliminate. It's just there, the messiness of the real world.
Makes sense. So you can't aim for zero error. Okay, the dartboard analogy helps here. High bias, underfitting. That's like all darts landing together, but way off the bullseye.
Exactly. Consistent, but consistently wrong. Systematic error.
And high variance, overfitting.
Darts scattered all over the board. The model learned the noise, the random fluctuations in the training data, not the real pattern.
So we need to balance them. Find that sweet spot of model complexity.
That's the game. Minimize the sum of the two.
Which needs a process to find that minimum. That brings us to optimization, gradient descent, or GD. the blindfolded person walking downhill analogy.
You have stepping opposite the gradient towards the lowest point of the cost function. Simple idea.
But we don't usually use plain GD, right?
Not for big data sets, no. The standard is mini-batch gradient descent, MBGD. It's the practical choice.
And why is that?
It's a compromise. More stable than stochastic GD, which uses just one sample that's noisy. Faster and more efficient than batch GD, which uses the whole data set that's slow. Mini-batch gives you a good balance, plus it works great with modern parallel hardware.
Okay, optimization sorted. Now, something crucial for deep learning specifically, nonlinearity. Why is that essential? Why can't deep networks just be linear?
Good question. It boils down to math. If you only used linear activation functions, stacking layers, even hundreds of them, it would all mathematically collapse.
Relapse.
Yeah, it becomes equivalent to just having a single shallow linear layer. You lose the whole benefit of depth. Nonlinear functions like ReLU are what allow the network to bend and curve to learn those really complex decision boundaries you find in real data.
Without nonlinearity, depth is pointless. Got it. Okay, final piece. Regularization. Fighting overfitting. That high variance problem. L1 versus L2.
Right, key tools. And the geometric view really helps understand the difference. L2, ridge regression, its constraint is like a smooth circle. It pulls weights towards zero, shrinking them.
Towards zero, but not necessarily to zero.
Exactly. But L1, lasso, its constraint is a diamond. Sharp corners, right on the axis. And because optimization often hits those corners,
It forces weights to become exactly zero.
precisely. That's L1 doing automatic feature selection. It creates sparse models by zeroing out less important feature weights. It's the geometry doing the work.
Fantastic. So the three pillars: generalization through bias variance, optimization with mini-batch GD, and nonlinearity enabling depth. That really covers the core concepts.
It gives you the framework. And maybe one final thought, shifting to validation.
Go on.
The absolute integrity of your final result depends on one piece of discipline. Never, ever use your test set during model tuning or development. Keep it locked away until the very end.
Because otherwise you introduce look-ahead bias. You're implicitly tuning on the final evaluation data.
You got it. That final test score becomes meaningless. The method of validation is just as crucial as the model architecture itself. Remember that.
But always remember, the first step is diagnosing the error. Knowing the problem dictates the solution.
That definitely clarifies the core mechanics. Okay, here's something to think about as we wrap up. Even if you follow all this, you tune your model perfectly, why is relying on just one single split of your data into a training set and a test set actually a pretty unreliable way to estimate how well your model will really perform out there in the wild? Think about the variability that single split introduces. We'll leave you with that. Welcome to the Deep Dive. You asked for a closer look at intermediate data science concepts, so we've gathered the sources.
Yeah, and today our mission is really getting into the nitty-gritty, the mechanics behind stability, generalization, and reliable evaluation in machine learning.
Exactly. We want to unpack some of the secret sauces, like how we actually train these super deep networks or avoid misleading results.
We're definitely moving past the basics. Think fundamental problems. Why deep networks initially fail to train. Why accuracy can sometimes be, well, dangerously wrong. We'll hit on ReLU, batch norm, regularization.
And ensembles, right. Okay, let's start with that first big hurdle, the vanishing gradient problem. Why were functions like tan causing such issues?
Well, the core issue is the derivative. With tan, the derivative's always less than 1. So during backpropagation, you're multiplying these small numbers over and over again across many layers.
And that signal just fades out.
It shrinks exponentially. So the layers near the input, they basically stop learning anything useful. The gradient vanishes before it gets there.
Right. And then came ReLU, the rectified linear unit. A simple idea, but it changed things.
Hugely. Because for positive inputs, its derivative is exactly 1. No shrinking. The signal passes right through. That's what let us build much, much deeper networks.
But it's not perfect, is it? There's the dying ReLU issue.
True. If a neuron's input consistently goes negative, it can get stuck outputting 0 and never recover. It's a trade-off.
So how do we manage that?
Well, the benefit of stopping the vanishing gradient usually outweighs the risk. Plus, there are techniques like careful initialization or using variants like leaky ReLU to mitigate it, but the main win is that non-saturating gradient.
Okay. And that brings us to the other big stability player, batch normalization, BN.
Right, BN. It tackles something called internal covariate shift, or ICS.
Which, in practice, means?
Imagine each layer in the network is trying to learn, but the distribution of the data it receives from the previous layer keeps shifting around during training. It's like trying to hit a moving target.
Ah, okay. So BN locks that target down a bit.
Exactly. It normalizes the inputs to each layer, making those distributions more stable. And a really key side effect is that it lets you use much higher learning rates.
Oh, interesting. So faster training, too.
Significantly faster. That stability is crucial.
Okay, so stability helps. Now, let's shift to making sure models generalize perform well on new data. Regularization is key here. L1 versus L2.
Yeah, the two main ones. L2, or ridge, penalizes the square of the weights. It shrinks all weights towards zero, kind of gently.
And L1, lasso.
L1 penalizes the absolute value of the weights. The math works out so it can force weights of less important features exactly to zero.
So it does feature selection automatically.
Precisely. You'd use L1 if you suspect many features are irrelevant and you want a sparser model, high-dimensional data, for instance.
Got it. And in neural networks, there's also dropout. How does that work?
Dropout is clever. During training, you randomly switch off or drop a fraction of the neurons in a layer.
Why would you do that?
It prevents neurons from becoming too dependent on each other, what the sources call co-adaptation. It forces the network to learn redundant representations, making it more robust.
So it's like training many smaller networks at once.
Kind of. It's like training a huge ensemble of two-nuller subnetworks that share weights. It really boosts generalization.
Now, the crucial bit, trusting the results. K-fold cross-validation instead of just a single train test split. Why is that better?
A single split can just be lucky or unlucky, you know? With K-fold CV, you split the data into K parts, or folds. You train on K1 folds and test on the remaining one, rotating through until every fold has been the test set once.
So every data point gets used for testing.
Exactly. It gives you a much more stable, reliable estimate of how your model will likely perform on unseen data. Less chance of being fooled by a single split.
Makes sense. Which leads to the imbalanced data trap. Things like fraud detection, where the event you're looking for is rare. Why can standard metrics like ROC, AUC be misleading there?
Okay, so ROC, AUC looks at the trade-off between true positive rate and false positive rate. The problem is the false positive rate's denominator includes all the actual negative cases.
And if there are tons of negative cases.
Right, like 99.9% non-fraud. Getting most of those right, true negatives, massively inflates that denominator, making your false positive rate seem tiny, even if you're misclassifying a lot of the rare positive cases. It gives this overly optimistic view.
Dangerous if finding those few positive cases is critical. So what's the fix?
Focus on metrics that care primarily about the positive class. The go-to is the precision recall PR curve.
How does that help?
PR curves plot precision against recall. They only use true positives, and false negatives. They completely ignore the true negatives.
Ah, so they aren't skewed by the huge number of easy negative examples.
Exactly. They give you a much more realistic picture of performance when correctly identifying that rare positive class is what truly matters.
That's a really important distinction. Wow, okay, so we went from gradient fixes like ReLU and BN through generalization with L1, L2 dropout and ensembles, right up to validation with CV and PR curves. Quite the journey.
It really covers some core techniques for building models that, actually work reliably.
So what's our final thought for listeners to chew on?
Well, we talked about improving classifiers, and techniques like PCA, principal component analysis, are often used for dimensionality reduction. They work by finding the directions of maximum variance in the data.
Right, keeping the most spread out information.
But here's the thing. Maximum variance doesn't always mean maximum separation between classes. What if the crucial information that distinguishes Class A from Class B actually lies along an axis with very little variance?
Huh. So maximizing variance might actually throw away the most important classification signal.
It can happen. So the question to ponder is, when you're building a classifier, is simply maximizing data compression or variance always the right goal? Or do you sometimes need methods that explicitly look for separation, even if it's not where the most variance is?
Welcome to the deep dive. We're skipping the intros today and jumping straight into some pretty advanced stuff in data science theory. The goal here is to get beyond just the definitions you see everywhere and really dig into the core ideas.
Yeah, we're going to look at some fundamental model types, maybe bust a few myths about how deep learning optimization actually works, and talk about the engineering needed to keep these huge models stable.
Okay, so let's kick things off right at the foundation. This split between generative and discriminative models, it sounds like it's all about probability.
Exactly. It boils down to what part of the probability puzzle they're trying to solve. So a generative model, it's ambitious. It learns the whole thing, the joint distribution PXY.
Meaning it learns how the data features X and the labels Y occur together.
Precisely. And because it understands that relationship, it can actually generate new data points. Think like Janins creating images or VAEs. It's building a model of the world, essentially.
Okay, so world builders versus, what's a discriminative approach then?
Discriminative models are much more focused. They only care about PYX.
The probability of the label given the input.
Right. All it needs to know is, okay, I see this input X, what's the chance it's label Y? It's purely about distinguishing between classes, not generating them. Think your standard deep classifiers.
And this choice, it affects the kind of loss function you'd use. Like cross-entropy gives you actual probabilities.
Yeah, cross-entropy loss aims to give you calibrated probabilities outputs that actually reflect the true likelihood, PYX. But then you have things like max margin loss, like in SVMs.
Right, Mahon's loss.
Exactly. That one doesn't really care about probabilities being perfectly calibrated. It's all about pushing that decision boundary as wide as possible, maximizing the margin.
So it's sacrificing maybe some statistical nuance for just raw classification robustness.
You could put it that way. It's solving a slightly different problem, boundary maximization, not probability estimation. Both useful, just different goals.
Okay, that distinction makes sense. But when we actually try to train these deep models, things get messy. Yeah. Which brings us to maybe the biggest myth when I'm training a model.
Think of the loss function as this incredibly bumpy, complex terrain you're trying to find the lowest point in. Without batch norm, it's full of sharp cliffs and really unpredictable slopes. You have to take tiny, careful steps, a small learning rate.
Okay.
Batch norm essentially sands down those cliffs. It improves the mathematical properties like Lipschitzness and gradient smoothness. This lets you take much bigger, more confident steps.
So you can crank up the learning rate without the training exploding.
Exactly. And that drastically speeds up convergence. It's about enabling faster training by making the loss surface easier to navigate, not primarily about fixing shifting distributions mid-network.
Fascinating. So we engineer stability there, but then there's this other thing that seems to break all the rules.
Yeah.
Double descent.
Right. This one's really counterintuitive from a classical stats perspective.
Yeah, the idea that test error goes down, then up as the model gets complex enough to fit the data, but then it goes down again when it gets massively over-parameterized.
That's the one. It peaks right at that interpolation threshold where the model just fits the training data perfectly. And then, yeah, performance gets better again as you add way more parameters than you seemingly need.
Why does that happen? It feels like massive overfitting should just keep getting worse.
It's a super active area of research. But the leading idea is that in this highly overparameterized regime, the optimization algorithms we use, like SGD, have an implicit bias. They tend to find flatter minima in that vast loss landscape.
Flatter minima, meaning solutions that are less sensitive to small changes in the input.
Sort of, yeah. These flatter solutions tend to generalize better, even though the model has enough capacity to memorize every single training point, including noise. So using huge models isn't just okay, it might actually be beneficial because optimization finds better generalizing solutions within them.
Wow, okay. That explains a lot about why people use such enormous models.
Yeah.
Let's shift gears slightly to deliberate engineering for stability. The transformer architecture is a great example, right? Specifically that scaled dot product attention.
Absolutely. That little scaling factor, dividing by the square root of dk, the key dimension, that's crucial.
What problem is it solving? Why divide by that specific value?
It's all about controlling variance. When you compute dot products between high-dimensional vectors like the query Q and key vectors in attention,
which can be hundreds or thousands of dimensions long.
Right. The variance of that dot product scales linearly with the dimension, dkp. If you don't control that, the dot products can become huge.
And if those values going into the softmax function are huge.
The softmax saturates. It outputs values very close to 0 or 1, and the gradients become tiny, almost 0.
Which means the model stops learning effectively, vanishing gradients.
Precisely. So that division by the square root of dk is specifically designed to normalize the variance of the dot product back down to 1, regardless of the dimension.
It keeps the inputs to the softmax in a sensible range where gradients can actually flow.
Exactly. It's a calculated move, pure variance control, to ensure stable training for these deep attention mechanisms. It's essential engineering. Looking back at batch norm, double descent, finding flat minima, and this attention scaling. There's a common thread, isn't there? It's all about deliberately managing or benefiting from the scale and variance of activations and gradients to make optimization work.
Yeah, stability seems to be the name of the game, often achieved through these clever, sometimes counterintuitive mathematical tricks or implicit biases. So, building on that idea of stability and how models learn, here's a final thought for you to chew on. Think about catastrophic forgetting. That's when a model trained on one task completely forgets how to do it after you train it sequentially on a second task. It highlights how fragile that learned knowledge can be. Maybe look into some of the ways people try to fight this, things like elastic weight consolidation, progressive neural networks, or even replay techniques. How do we build models that learn and retain? That's a huge ongoing challenge.